Okay, we're on to question 3, and question 3 is about moments. Okay, so you can see here's the pivot, okay, and the distance from the pivot to the force there is marked as 84 centimeters. Okay, it's asked us to calculate the moment of the force, so we need the formula moment of force is force times y perpendicular distance from the pivot. Okay, the force is 480 newtons. Okay, and then the distance is 0.84. Why? Because this is 84 centimeters, so we need to convert that into meters. Okay, so if we work it out on a calculator, we get 403.2 Newton meters, okay, which is approximately equal to 400 Newton meters, which is what they asked us to prove in the question. Okay, the force F is the minimum force needed to start opening the gate. Okay, and you can see that, there we go, there's the force there, and there's the distance to the force right there. Okay, now just before the gate opens, then the anti-clockwise moment and the clockwise moment are going to be balanced. So the clockwise moment, okay, so the moment clockwise that's caused by F is going to balance the anti-clockwise moment from the spring. Okay, if we go a little bit bigger than that, okay, then the gate's going to start opening, right? So that's what they're asking us for there. Now there's two ways that we can do this. We can either say, okay, you know, when the sum of the clockwise moments is equal to the sum of the anti-clockwise moments, then this means that it's going to be balanced. Okay, and in this condition here, then that means that the clockwise moments is going to be equal to the anti-clockwise moments. We've just calculated the anti-clockwise moments. That's 400 Newton meters there. So we know that. And then that's going to be the force times by the perpendicular distance from the pivot. We know the perpendicular distance from the pivot. That's 3.2. Okay, times by the force, okay, equals 400 Newton meters. Okay, so if you put that into a calculator, you'll find out that the force is about 126. Okay, which, two significant figures, is going to be about 130 newtons. So that's one way that you could do it. Or, you know, at this step here, you can say, okay, I know a formula for this, and that this is Fc times by dc equals Fa times by dA. Okay, and then just substitute in the numbers that you've already done, right? Okay, so the anti-clockwise was 480 times by 0.84. Okay, clockwise was times by 3.2. Okay, and it's Fc that we're trying to find. Okay, and again, if you put all of that into a calculator to two significant figures, your answer is going to be 130 newtons. Okay, final part, the spring is removed for testing. Explain what happens to the spring if the force applied to extend the spring is too large. Okay, so this is where we need to remember our Hooke's law graph. Okay, and we'll remember that force is directly proportional to extension, okay, until we reach this point here, right? And then it's no longer proportional, right? So this here is the elastic region of the graph, and this here is the plastic region of the graph. And the this dotted line between the two is what we would call the elastic limit. So if the force applied is too large, then that means, you know, if we're going to go out of this region here, we're going to go into a region where the force is too large. That means that we're going to exceed the elastic limit, right? And if that happens, we end up in the plastic region. And the plastic, what does plastic mean? It means that it won't return to its original shape anymore. It will be permanently deformed. Okay? even when you remove the force, the deforming force, it will stay permanently deformed.